Hello and welcome back. This is a short tutorial on scientific measurements with a specific emphasis on significant figures. So as you can see here, we have a number of scientists and medical workers taking measurements in the field or in a doctor's office, and ultimately they need to write those measurements down and communicate with other scientists or other people that work in the field with a certain level of precision. So we're going to talk about how you take a measurement and then how we determine which of, if we're reading somebody else's measurement, which one are significant figures. So that's the goal of this short tutorial. So in terms of error, I have 3 bullet points here, maybe 4, just to kind of introduce this idea of what a significant figure is. And oftentimes students are a little confused by this term, significant figures. And really it's about making sure that we understand how measurement is taken and how we know, what number of digits to write down from a measurement. So, for example, because each measurement involves an estimate, the measurement always has an error. So, in other words, when we take a measurement or when a scientist takes a measurement, there is some human error involved. And I'll give you an example. We'll talk a little bit about that in a few minutes. So secondly, we record all measured numbers, including the first estimated digit. So this is kind of how we go about taking a measurement. You're going to write down all the measured numbers that we know with certainty, and we're going to estimate one more. It's in that estimated digit that there's some human error. These digits are called significant digits or significant figures. So the ones that we write down, if we're using a thermometer or piece of glassware in the laboratory, a ruler, some other tool that takes measurements, we use this process where we write down the digits we know with certainty, we estimate one more. All of these digits are referred to as significant figures. And another term is exact numbers. These have an infinite number of significant figures. So I'll just give a quick example. I might count the number of people in this course, for example, and say, all right, we've got 32 people in the course. That looks like it only has 2 significant figures, but really because we don't take fractions of people, we're just counting numbers of people. We could say that this number is an exact number and has an infinite number of significant figures. So for example, I could put a decimal point and write sort of an infinite number of zeros behind that number. It doesn't change the number 32. It just means that there's an infinite number of significant figures with regard to if this was considered a measurement. All right, now let's look at an example of how a scientist might read a tool of some sort in a laboratory and write down the correct number of significant figures. If these are 2 thermometers, let's take a look at how many digits we would write down if we were taking a measurement from these 2 different thermometers in a laboratory. We'll start with the one on the left. So the one on the left here, if we look closely, has increments between 20 and 30. So it looks like each increment is a single digit. So we have 21, 22, 23, 24, 25, and so on up to 30. So if we were to measure the red liquid inside this thermometer, we would say, okay, we know with certainty that it goes up to 21. So here's 21. So I'll write that down. 21. And now we're going to estimate one more digit. So this is between 21 and 22. So here and here. So we're estimating how far up that red liquid goes between 21 and 22. And we're going to estimate it. There might be some error here. So I might put down 21.2. Somebody else might say 21.3. So there's some error that's in this digit here, the last digit that we're writing down. And that's the known way that we take a measurement in a laboratory. So we can say that this measurement has 3, and I'll just abbreviate as sig figs for significant figures. So this tool here, this thermometer, allowed us to obtain 3 significant figures with our measurement, and we know there's some error associated with it. Let's go over to the right thermometer. So on the right-hand side, this tool looks like we have more increments involved. So we have more tick marks, in other words. So here we have between 20 and 21 and then all the way up to 22, but we can zoom in now and see these additional tick marks. So we can say with certainty with this thermometer that it goes up to 21.123. So we know with certainty to 21.3. Okay, so if I was taking down this measurement, but the process is that we estimate one more digit. So notice that the red liquid goes just above the 0.3 mark on this particular thermometer. So we're going to go ahead and estimate, and I might say 21.3, somebody else might say 21.32, something of that nature. But what you can see here is that we were able to write down 4 sig figs using this tool. Okay. So this tool on the right, this thermometer on the right, allowed for 4 significant figures, and this one on the left gave us 3 significant figures. So when we write down a measurement, we're actually communicating to other scientists about the precision that we can get from our tool, and it's important that we all do it the same way. So just to reiterate, you write down the number of digits that you know with certainty, and then you estimate one more digit. So I think I have a few bullet points about this. Using the first thermometer, the temperature is 21.3. So this bullet point, or this person went with the 3, that we got one of those there. And then the other, there's 3 significant figures. And for the second thermometer on the right, we have 21.32 degrees Celsius, which we did over here with the 4 significant figures in that case. All right, that's the process. Now we're going to move on to looking at what we call the rules for significant figures. And these rules are laid out so that when you are interpreting a measurement that another scientist or medical worker of some sort made, that you can read that measurement and know the precision that was used with the tool that particular scientist used. So we're all using the same way of writing down measurements, so then when we read somebody's measurements, we should have a good idea of how many significant figures are in the number. Sometimes it's not so easy to know how or to count zeros. So these rules that we're about to talk about are really for interpreting measurements and thinking about whether a zero is significant or not. So let's look at these rules. The first one is that all non-zero numbers are significant. So that's pretty straightforward. If you don't have a zero, if we just have 1, 5, 6, 3, so 1,563, they're all non-zero. They're all significant. So this would have 4 sig figs. This rule also states that zeros between non-zero numbers are significant. So what that means is that if you have 1, 0, 0, 3, something like that, 1,003, those 2 zeros are between 2 non-zero numbers, and so they are significant. So this would also have 4 sig figs. All right, that's the first rule. That one's pretty straightforward. Next one, trailing zeros always count as significant if a number has a decimal point. So the trailing zeros are often challenging to know what to do with, but they are always significant if they come after the decimal point. So let's say we have a measurement that's 1.300, 1.300. So those 2 zeros there are considered trailing zeros, final zeros, and there's no other reason to put them there other than to share with other researchers that you measured to the thousandths place here. So they are significant. Those 2 zeros are definitely significant. They're called trailing zeros with a number that has a decimal point, and they're definitely significant. Another set of trailing zeros are not significant. So these are the zeros that are a part of a number that does not have a decimal point. So if I say, for example, there's 25,000 people in CenturyLink Stadium last night. There's no decimal place in this particular measurement or number, and there's no reason to think that these zeros are significant. They're actually just placeholders. So those are not significant zeros. This number only has 2 significant figures. The zeros are not significant in this case. Final rule is that leading zeros to the left of the first non-zero digit are never counted as significant. So this is only true or only a situation that comes up when we have a number with a decimal. So we have something like 0.00591, something like that. So here are these leading zeros, and they're to the left of this first non-zero digit. So these zeros here are not significant. They're just placeholders. So you would want to say that this number only has 1, 2, 3 significant figures. Okay. All right, those are the rules, and we're going to practice that now. So this is one of the take-home kind of skills of this particular tutorial. So let's practice, and then I'll let you move on to do some of your own practice problems off this video. So the question here is, how many significant figures does each of the following numbers have? We're also going to convert these numbers to scientific notation. So we'll do both of those tasks at one time. So the first one is this first number here, 4.1397. Notice that there's no zeros, so they should all be significant. So if we just count, we've got 1, 2, 3, 4, 5 significant figures. So the answer to how many is 5. And now let's put this in scientific notation. Notice that we're going to have to move the decimal place 2 places to the left. So we get 4.1397 times 10 to the second as our scientific notation. So we move their decimal 2 places to the left. All of those digits are significant, so we leave them in the notation. So let's look. We've got that number. That's correct. And we said 5. Nice work. All right, number 2. Number 2, here we have some leading zeros. Recall that those are to the left of the first non-zero digit, so they are not significant. So it looks like we only have one significant figure in this number. And all of those zeros are then going to drop out when we convert this to scientific notation. So let's move our decimal. We've got 1, 2, 3, 4. We're moving it 4 places to the right, so we're going to have times 10 to the negative 4, and it's just going to be 6. 6 times 10 to the negative 4, because we're losing all of those other zeros. They're just placeholders. And we should only have one significant figure. So let's see how we did. There's our scientific notation, and we have one sig fig. All right, number 3. Looks to me like all of these digits are significant because here we've got zeros, but they're between 2 non-zero digits, so they also are significant. So if we count, we've got 1, 2, 3, 4, 5, 6, 7 significant figures. And it looks like we're already in a pretty okay notation. So I don't think we need any changes here. So we're just going to write that number out as it is. And we should have 7 sig figs. There we go. All right. And the next one, 161,000. These zeros are trailing, but there's no decimal, so they are not significant. So we're going to drop those out of the scientific notation, but we're first going to count how many times to the left we have to move the decimal. So if the decimal's here, we're going to move it 1, 2, 3, 4, 5. So we're going to have 10 to the 5th. We'll have 1.61, drop the 3 zeros, times 10 to the 5th, and we should have only 1, 2, 3 significant figures. There's 1.61 times 10 to the 5th. The zeros are dropped, and we have 3 sig figs. There we go. The last one's a little bit different, but I wanted to make sure to point this out. Sometimes we get a number that has these, what we would call trailing zeros with no decimal, but we can put the decimal there, even though we don't have anything to the right of the decimal, we can put that decimal there to say that, to indicate that these zeros are significant. So if you're interpreting a number that has a decimal place that looks like this, the point of that decimal place is to say that those zeros are significant. So that means we have 1, 2, 3, 4 significant figures. And if we move the decimal 1, 2, 3 places, we're going to have 3.600. We don't drop the zeros because they're significant.